In the last lecture, we have done one theorem called as Modulation Theorem. So that you can say it was a fifth properties of our Fourier Transform. So next sixth properties is that if f of x is equals to f of s, then f of x of n f of x is equals to minus of I raised to n dn upon ds of n into f of s. So we have to prove this. So how we will proceed? So first we will write as per our definition what we know. We know that f of s is equals to 1 upon square root of 2 pi integral minus infinity to infinity e raised to I sx f of x dx. Okay, so we can also write is equals to I of n 1 upon square root of 2 pi integral minus infinity to infinity x of n e raised to I sx f of x. So which we can write it as I raised to n f of whole thing, it will be f of x of n into f of x, or we can also write this thing as f of x of n into f of x is equals to minus I square n dn f of s upon ds of n. Hence we have proved. Okay, so now seventh property, where f dash of x is equals to I s f of s if f of x tends to 0 as x tends to plus or minus infinity. As a result, so what we have to prove first is, just see, f dash of x is equals to what it will be, 1 upon square root of 2 pi integral minus infinity to infinity e raised to I sx f dash of x dx, or 1 upon square root of 2 pi integral minus infinity to infinity e raised to I sx the derivative of f of x, it will be dx. Okay, so next step it will be is equals to 1 upon square root of 2 pi e raised to I sx, then f of x we have taken out, it will be minus infinity to infinity e raised to I sx f of x into dx, or else 1 upon square root of 2 pi, first part it will be 0 minus is will come out, it will be minus infinity to infinity f of x into dx. One more term is there, is, this is there, so is so as a result what we are getting it here is minus is f of s, hence proved. It's a simple two-step proof. So we have to prove is f dash of x is equals to is f of s. So we know the here that definition of Fourier transform. This is with respect to f dash. So same thing we have written, and then what we have done is that f dash we have written with d f of x. Then 1 upon square root of 2 pi. This we have taken out. And then we have solved this and we have got this proof. I hope this proof is clear for you what we have done in this. Okay, last now the least property which we have to solve here. It's the f of integral a to x f of x dx, okay, which is equals to f of s divided by minus of I of s. Okay, so let me start the proof for this. So proof is f1 of x is equals to integral a to x f of x dx. Okay, so we will be getting something like f1 dash of x is equals to fx. See, we have marked this one as 1. Okay, what we have got is that f dash of x is equals to is f of s. Okay, so f dash of x is what? Minus I s f of, here it is with respect to 1, right? So it will be f1 of s, we are referring this. So you can mark this as from 1. Okay, now we can write this thing further, this step as like minus I s. This you can write it as f of f1 of x. Now we will solve this. So that is equals to minus is f of integral a to x f of x dx, a to x f of x dx. So as a result, f of integral a to x f of x dx is equals to 1 upon minus is f of f dash of x, which is equals to 1 upon minus is f of x, which is equals to f of s upon minus is. I hope these things are clear what we have done in this. So hence we have proved, we have completed our proof. So that's it, we have done all our properties of Fourier transform. So if you'll have a look what we have done in this. So when we have started the properties of Fourier transform, so first property was linear property. What was meant by linear property? Second property, it was a change of scale of property. Then third property was shifting property. Fourth was this expression. Then the fifth was a modulation theorem. Sixth was this one, f of x is equals to f of s. Then this term. Then the seventh, eighth. So there are 8 properties of a Fourier transform. Okay, so That's it, and thanks for watching.